Well, dear students, now we shall consider force between two straight parallel conductors of infinite length carrying current along same direction. Okay, let's understand the force between two straight parallel conductors of infinite length carrying current along the same direction. Force between two straight parallel conductors of infinite length carrying current along the same direction, Let me consider two conductors. This is conductor 1 and this is conductor 2. See, this is carrying current I1 and this is carrying current I2. These two conductors are separated by a distance d. In air, in free space, in air or vacuum. See, what is the magnetic field at this point, at some point P here, due to current carrying conductor? Magnetic field at a point, distance d from conductor 1, first conductor, is B1 is equal to mu naught by 4 pi, or you can write mu naught by 2 pi I1 by D. Let me call this as equation 1. See, that is the magnetic field acting this point by these conductors. Let me take this field as it is acting in this direction, B1. The current carrying conductor 2 experiences force due to magnetic field of conductor 1. As a result, it experiences a force like this. See, this is force acting on conductor 2 due to conductor 1. The force acting on conductor 2 due to magnetic field B1 is this is equal to F21 equals I take the force as maximum force. So what is the maximum force experienced by a current carrying conductor in the magnetic field? It is B into I into L. See, here instead of place of B I write B1, I2, L. Say this conductor is of infinite length. These two conductors are of infinite length. Okay, I just take a particular length L. say this, let this be L. This particular length is I taken as L. What is B1? Using equation 1, F21, force acting on conductor 2 due to magnetic field of B1 is given by mu naught by 2 pi I1 into I2 into L divided by D, or F21 by L is equal to mu naught by 2 pi I1 into I2 divided by D. Let me call this as equation 3. Similarly, what is the magnetic field at this point due to current flowing in this conductor? See, it is acting like this. This is the magnetic field B2. And because of this magnetic field, this conductor also experiences force like this. Okay? It also experiences force like this. This is the, using left hand rule, you can write like this. Say middle finger points the direction current, and this is the direction of magnetic field, and this is the force acting. And here this is the force acting, this is the direction of current, the magnetic field is inside. Okay, see, this is what force acting on first conductor due to second conductor, due to magnetic field of the second conductor. Therefore, similarly force acting on conductor 1 due to magnetic field B2 is F12 is equal to B2 I1 into L. What is this B2? Mu naught by 2 pi I2 by D into I1 into L, or F12 by L is equal to mu naught by 2 pi I1 into I2 divided by D. This is equation 4. So when you compare equation 3 and 4, you can write from 3 and 4, F21 by L is equal to F12 by L. If you take only the magnitude, okay, C is equal to F by L. Therefore, F by L is equal to mu naught by 2 pi I1 into I2 divided by D. See, this is force per unit length acting on two straight parallel conductors carrying current along the same direction. From the diagram, you can find that these two conductors attract each other. If the current flowing along the same direction, the conductors will attract each other. Please see the direction of force. So use left hand rule. It is also called motor rule. Here forefinger points the magnetic field, middle finger points the current flowing in a conductor, thumb points the direction of motion of the conductor or direction along which force acts. Is in this case current flowing in this direction, magnetic field is towards you, and this is the direction along which force acts. And when you take this, see, this is the direction of current, this is the force, this is the direction of current, this is the direction of magnetic field. It is into the board, it is towards you, It is towards you, away from the board. It is away from you into the board. This one. See, because of the magnetic field of first conductor, the current carrying second conductor experiences this much of force. Similarly, due to magnetic field of the second conductor, the current carrying conductor experiences a force F12. See, they are equal in magnitude. That's what we have found. And because of that, they attract each other. So the direction of force indicates that they will attract each other. There is a force of attraction between them. If the current flows in the conductor in the opposite direction, then they will repel each other. They move apart from each other. They are trying to move away from each other. If the current is in opposite direction, they repel each other. If the current is along same direction, then they will attract each other. Okay. See, this is the conclusion which is drawn from this equation. Using this equation, we can define what is ampere. In fact, ampere, the unit for electric current, is defined on the basis of this equation. Let's understand how it can be defined. How it can be defined. So now let me take the equation F by L is equal to mu naught by 2 pi I1 into I2 divided by D. If D is equal to 1 meter, F by L is equal to 2 into 10 raised to minus 7 Newton per meter. Then I1 is equal to I2 is equal to 1 ampere. See, therefore, ampere is that steady current which, when flows through two straight parallel conductors of infinite length separated by a distance of 1 meter in air or vacuum. Ampere is that steady current which, when flows through two straight parallel conductors of infinite length carrying current along the same direction separated by a distance of 1 meter, experiences an attractive force of 2 into 10 raised to minus 7 Newton per meter. Ampere is that steady current which, when flows through two straight parallel conductors of infinite length separated by a distance of 1 meter, having the same direction in both the conductors, then they will attract each other with a force of 2 into 10 raised to minus 7 Newton per meter. See, this is the definition of ampere. See, therefore, how we can define ampere? Ampere is that steady current, which when flows through in the same direction, through two straight parallel conductors of infinite length separated by a distance of 1 meter in air or vacuum experiencing an attractive force of 2 into 10 raised to minus 7 Newton per meter. See, that is said to be 1 ampere. Ampere is that steady current which when flows in the same direction through two straight parallel conductors of infinite length, separated by a distance of 1 meter in air or vacuum, experiencing an attractive force of 2 into 10 raised to minus 7 Newton per meter. See, that is what we call it as ampere. So, in fact, this definition has been adopted in SI. Okay, before that we used to say if the rate of flow of electric current through any section of a conductor is 1 ampere per second, then the corresponding current is said to be 1 ampere. But later, say this is considered to be the standard definition for ampere. If you consider motion of two charged particles parallel to each other, they will repel each other, they won't attract each other, because electrostatic force is greater than magnetic force. Electrostatic force of repulsion is greater than magnetic force of attraction. So therefore, in that case, two charged particles moving along same direction parallel to each other, they repel each other. While two current carrying conductors having current flowing in the same direction will attract each other. See, that's the difference between charged particle and current carrying conductor. So now let us understand magnetic field due to a current flow. Magnetic field due to a current flow. So let me consider a loop carrying current in the anti-clockwise direction. Okay, if there is a point P somewhere here, this is the radius and the distance of point P from the center is x. Then magnetic field at P we have derived in the previous classes. Magnetic field at P is given by B is equal to mu naught by 4 pi 2 pi n I a square ni 2 pi ni r square by r square plus x square whole to the power of 3 by 2. Here pi r square I take it as a area. See, therefore B is equal to mu naught by 4 pi 2 into n into I into a divided by r square plus x square whole to the power of 3 by 2. For x far greater than r, if the point P is far away from the center of the coil, see, in such a case r square plus x square approximately equal to x square. See, therefore the equation takes the form B is equal to mu naught by 4 pi 2 into n into I into a divided by x square to the power of 3 by 2, or this is v is equal to mu naught by 4 pi. See, this is, I take this as m, 2m by x cube, where n into I into a is equal to m, called magnetic dipole moment. Magnetic dipole moment. Magnetic dipole moment. Therefore, this equation tells you that a current carrying loop acts like a magnetic dipole. Even in this case also discussed in the previous derivation itself. After this derivation, as a special case, we came to that conclusion. For sake of completion, I am once again repeating this. So therefore, when current flows through a coil in anti-clockwise direction, this phase behaves like a north pole and the other phase behaves like a south pole. Poles are always occurs in pairs. So even with a current carrying conductor, you cannot get isolated north or isolated south polarity. Even in case of a current carrying conductor, magnetic poles always occurs in pairs. Okay, that's the conclusion. And this magnetic dipole moment is a vector quantity. What is its unit? SI unit of m. It is a vector quantity. SI unit of m is, for current ampere, for area meter square, is ampere meter square. That is the SI unit. Now let us understand the torque acting on a current loop in an external magnetic field. So now we shall consider, in an external magnetic field, if you keep a current loop, what is the torque acting on it? Torque acting on a current loop kept in a uniform magnetic field. Kept in a uniform magnetic field. So let me consider a magnetic field, external magnetic field. See, in this external magnetic field of strength V, uniform magnetic field V, I am keeping a current carrying loop. Keeping a current carrying loop. Let this loop is of length L and breadth B. Let L be the length of the loop and B be the breadth of the loop. Okay. Now let I be the current flowing through this loop. PQRS. Let I be the current flowing in this loop. Okay. What is the force acting on this loop? See, you just apply a Fleming's left hand rule to identify what is the force acting on it. See, this is the current flowing direction, this is the magnetic field, and this is the force acting. See, when you comes here, see, this is the direction magnetic field force acting. See, therefore, one force acting in this direction, another force acting in this direction. This is into, like this. Okay, it is into the board, it is towards you. So it is acted upon by a force. force, and this force acts only at the perpendicular sides PS and QR. See here, this part of the conductor is parallel to the field direction. It does not experience any force because you know that force is given by BIL sin theta. Here theta is 0. See, therefore this side PQ as well as RS does not experiences any force, while the sides which are perpendicular to the field experiences a maximum force, and that force is given by BIL. Here let consider a loop, a rectangular loop, PQRS carrying current I, kept in a uniform magnetic field B. Let the area of the loop A is equal to L into B, and see, because of this it will rotate, it will acted upon by a torque. The sides PQ and RS parallel to B, hence they does not experience any force. Only the perpendicular sides PQ and RS PS and QR experiences force, but PS and QR experiences maximum force. See, therefore force acting on them is given by B into I into L. That is the force acting. So you know that equal and opposite forces constitute a couple. The tendency of the couple is to rotate the coil, rotate the loop. Okay. See, it is acted upon by a torque. The torque acting on the loop is given by torque acting on the loop, and the loop is torque is equal to force into perpendicular distance. See, torque is equal to force is B into I into L, and perpendicular distance here is between these two B. See, this is equal to L into B gives you area. See, therefore B into I into A, or I can write torque is equal to I into A into B. What is I into A? I into A is, but I into A is equal to M. What is this? Magnetic moment. Therefore torque is equal to M into B. See, this torque is a maximum torque. This is the maximum torque acting on it. This is because this is the maximum force we have considered. Maximum force. So maximum torque acting on this is given by M into B. Suppose if the loop is making certain angle with respect to field direction. instead of this it is making certain angle. In such a case, say here the dipole moment acting in this direction, angle between, this is dipole moment, it is always perpendicular to the plane and towards you. Magnetic field is like this, so between them angle is 90. So therefore in general torque is given by m cross b, or torque is equal to mb sin theta into n cap, where n cap is the unit vector along the direction of magnetic moment. If the plane of the loop normal down to the plane of the loop, making an angle theta with respect to the field direction, then in such a case torque is given by mb sin theta. See, this is a particular case and it is the general case. Have you got my point? Always magnetic moment acts perpendicular to plane of the coil. The direction of the magnetic moment is like this, it is perpendicular to plane, it is like this. Magnetic moment always perpendicular to plane. So therefore in a uniform magnetic field, a current loop is acted upon by a torque. The tendency of the torque is to align the current loop parallel to the field direction. When the angle between M and B becomes equal to 0, no torque will act. Suppose if this is the magnetic field, if the loop is like this, such that M is also acting in the same direction as B. So in such a case, the torque acting on it is 0. On the other hand, if this is the magnetic field, the magnetic moment is acting like this. When they are anti-parallel, when these two are anti-parallel, then also torque acting on it is 0. Only when it is perpendicular to the field direction, it will experience a maximum torque. So before going to the next topic, let us solve one or two problems related to the topics we have discussed so far. Two straight parallel conductors separated by a distance of 10 centimeter in air carries a current of 2 ampere and 3 ampere respectively. If length of each conductor is 4 meter, then calculate calculate force of attraction between them, force of attraction between them. Force of attraction between them. See, there are two conductors. Okay, see, this is carrying current 2 ampere. Let me take it as I1, and this is carrying current 3 ampere I2. They are separated by a distance of 10 centimeter. D is equal to 0.1 meter or 10 centimeter. Okay, and what is the length? Length of the conductor is 4 meter. Length of each conductor is 4 meter. So we know that F is equal to mu naught by 2 pi I1 into I2 into L divided by D. See here what is mu naught? Mu naught is equal to 4 pi into 10 raised to minus 7 Henry per meter. I1 is 2 ampere, I2 equals 3 ampere, L is 4 meter, D is 0.1 meter. Now substitute all these values. We are going to get F is equal to 4 pi into 10 raised to minus 7 by 2 pi. I1 is 2 into 3 into 4 divided by 0.1. This is 2 into 10 raised to minus 7 24 divided by 0.1. See, this comes out to be 4.8 into 10 raised to minus 5 Newton. See, this is the force between the two conductors. Force between two conductors. See here, what kind of force? It is an attractive force. Have you followed? Now let us take another problem. Two straight parallel conductors carrying same current, separated by a distance of 5 centimeter, repel each other with a force of 6.4 into 10 raised to minus 6 Newton. If Newton per meter. Find the magnitude of current. Find the magnitude of current flowing through them. Okay. So here there is one conductor, another conductor, current is flowing in opposite direction, okay, because they are repel each other and they are separated by D is equal to 5 centimeter. Let me take I1 is equal to I, I2 is equal to I, then force is given by F by L is equal to mu naught by 2 pi I1 into I2 divided by D. See here they have given F by L is given how much? 6.4 into 10 raised to minus 6 Newton per meter. I1 is equal to I2 is equal to I. Then D is equal to how much? 5 centimeter. 5 into 10 raised to minus 2 meter. And you know the value of mu naught by 2 pi. This is equal to 2 into 10 raised to minus 7 Henry per meter. So now substitute all the values. You are going to get 6.4 into 10 raised to minus 6 is equal to 2 into 10 raised to minus 7 into I square. This is divided by 5. 5 into 10 raised to minus 2. See, this comes out to be I square is equal to 6.4 into 5 into 10 raised to minus 8 divided by 2 into 10 raised to minus 7. This is 3.2 or this can be written as 0.32 into 5. 1.6. I square is equal to 1.6. I is equal to root of 1.6 ampere. You please simplify this. Simplify this and find out I1 is equal to I2 is equal to root of 1.6 ampere. Please work out the value and write the final answer. A circular coil of radius 5 centimeter carrying a current of 2 ampere has 500 turns. Has 500 turns. Calculate the magnetic field. Calculate the magnetic field at a distance. Calculate the magnetic field at a distance 20 centimeter from the center of the coil along its axis. See here, we shall make the approximation. B is equal to mu naught by 4 pi 2 pi ni r square by r square plus x square whole to the power of 3 by 2. So you please use this relation and find out what is the magnetic field. Okay, you know the number of turns given, strength of the current is given, radius is given, all the data are given. So using that you just calculate. So that's one way. You please try this. The second way is that since x is very large compared to radius, okay, so I just go for approximation. B is equal to mu naught by 4 pi 2m by x cube. You please try and find out the value. I just go for this. See here, what is m? M is equal to n into I into a. What is n? N is 500 turns. I is 2 ampere. Current of 2 ampere is flowing. And what is area? Area is pi r square, pi 3.14. R square is 5 centimeter. Radius is 5 centimeter. 5 into 10 raised to minus 2 whole square. You please substitute and find out what is m. See, this is equal to how much? This is 500 into 2. So you will get 1000. 1000. This is 10 raised to minus 4. What remains? 10 raised to minus 1 remains 2.5. Right. See, this can be this is see, this gives you 10 raised to minus 4. There is 10 raised to 3, 2.5. 2.5 I just write like this, 0.25 into 10 raised to minus 2. 0.25 into 10 raised to minus 1. 10 raised to totally 10 raised to minus 2. What remains? 10 raised to minus 2 remains. Or this is 7.85 into 10 raised to minus 3 ampere meter square. Please check it up. See, here there will be 10 raised to minus 4. There is a 10 raised to 3 here. 10 raised to minus 1 remains. 25. This is I can write 25.25 into 10 raised to 2. 0.25 into 10 raised to 2. 0.25 is already 10 raised to minus 1 is there. 0.25 into 10 raised to 1. 10 raised to 1. Therefore, 0.25 into 10 raised to 1. See, therefore this comes out to be 7.85 ampere meter square. 7.85 ampere meter square. And here what is x? X is given by how much? X is at a distance 20 centimeter. 0.2 meter. You please substitute all these values and calculate. B is equal to 10 raised to minus 7, 2 into m, 2 into 7.85 divided by 0.2 whole cube. 0.2 whole cube. So this can be written as 2 into 10 raised to 8 into 10 raised to minus 3. 8 2 by 8 is 1 by 4. This is 10 raised to minus 3, 10 raised to minus 4 Tesla. Please check this answer. Check it up. a rectangular loop of length 3 centimeter and breadth 2 centimeter is carrying a current of 0.5 ampere kept in a uniform magnetic field of 2.4 into 10 raised to minus 2 Tesla. Calculate maximum torque acting on the loop. See, torque acting on the loop is given by M into B. What is M into B? N into I into A into B. Here only one loop. Here N is equal to what? 1. I is 0.5 ampere. What is the area? Area is equal to length into breadth 3 into 2 into 10 raised to minus 4 meter square. This is 6 into 10 raised to minus 4 meter square. And what is the strength of the field? B is equal to 2.4 into 10 raised to minus 2 Tesla. See, therefore, the torque acting on this is given by torque is equal to I is 0.5 area 6 into 10 raised to minus 4 and the magnetic field is 2.4 into 10 raised to minus 2. 7.2 into 10 raised to minus 6 Newton meter. See, this is the torque acting on current loop kept in a magnetic field. Okay. So this is about the torque. So let us consider one more problem on torque experienced by a current loop in a magnetic field. Let me take one more problem related to this. A square coil outside 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically. The coil is suspended vertically and normal vertically and normal to the plane, the plane of the coil, makes an angle of 30 degree with the direction of a uniform horizontal magnetic field, a uniform horizontal magnetic field, 0.8 Tesla. What is the magnitude of torque? What is the magnitude of torque experienced by the coil? What is the magnitude of torque experienced by the coil? Okay, to understand that, see in this case, see we have the plane of the coil. It is making certain angle. See, this is the coil. This is the direction of magnetic field. Say this angle they have given as theta. Let me take this angle as alpha. Okay. The normal which is drawn to this gives you the direction of magnetic moment. Okay. Let me say the current is flowing in this direction, like this. I just take this in another diagram. Okay, I just take this side PQRS. So let me say this is PQ. So they have given this angle as T alpha, and let me take normal drawn to this as M, direction of magnetic moment. Okay, so you know that it is acted upon by a torque, and the tendency of the torque is to align the loop, current loop parallel to the field direction. See, if this is alpha, I just take a triangle PQR, M here, N here. See, if this is alpha, this is also alpha. Then what is this? This side, this is force. This gives you force. See, what is cos alpha? Cos alpha is equal to adjacent side Qn divided by PQ. And you know that this is breadth B, this is breadth of the coil. See, therefore Qn is equal to B cos alpha. See, what is torque? Torque is equal to force into perpendicular distance. What is force? Maximum force is B into I into L, and perpendicular distance is Qn into Qn. I just write here cos alpha is equal to NQ divided by PQ. See, therefore NQ is equal to B cos alpha. Torque tau is equal to B into I into L. This is length. This is breadth. And the perpendicular distance here is B cos alpha. B cos alpha. L into B gives you area. N into B into, see this I take it as area. Cos alpha. See here, if I take this angle as theta, angle between magnetic moment and B, alpha can be written as 90 minus theta. Alpha is equal to 90 minus theta. Just for cos of 90 minus theta. See what you are going to get, N into BIA sin theta. Sin theta. This is torque. This gives you magnitude of torque. See, in our previous derivation, we have taken the normal drawn to the plane of the coil is at right angles to magnetic field. On the basis of that, we have derived the expression for maximum torque. If the plane of the coil makes certain angle with respect to the field direction, then in such a case, magnetic field will be in this direction and magnetic moment M is in this direction. The torque is acting here. This is the direction of torque. And torque is M cross B. M cross B. See, therefore, see here, torque is equal to BIA into sin theta. See, they have given N 20 turns. For N turns of coil, the torque is given by N into BIA sin theta. Now substitute for this. What is N? N is 20 and the strength of magnetic field is 0.8 Tesla. Current of 12 ampere is flowing in. And what is area? 10 centimeter square or 0.1 meter square. Sin 30. Sin 30. Say this comes out to be, you please simplify this. This is 16 into 12. 16 into 12 or 8 into 12. This is 8 into 12. Sin 30 is 1 by 2. (16 into 12 into 10 raised to minus 2 into 1 by 2). This is how much? You please substitute. .96 Newton meter. See, therefore, torque acting on the square loop is 0.96 Newton meter. Have you understood?